Thanks everyone for showing up, and hope that this will be an interesting talk for everybody. This talk is called PostgreSQL at 20 terabytes and beyond. And when I initially set up this talk, I went back and forth on whether to say 20 terabytes and beyond or 400 terabytes and beyond, because at that time, the largest database we had was 20 terabytes, but the whole analytics environment was 400 terabytes. Now, you note the date on the slides is January 2018. So a little bit of time's passed, and we'll talk about what's changed in our environment at the same time. But we've actually grown to over 600 terabytes in analytics data, and it keeps going up from there. So the first question probably some of you have is, what's the use case? What kind of data are we talking about? Why do you have so much data? Just as a market leader in mobile advertisement attribution and analytics, what we do is we take a stream of large amounts of mobile event data, and then we provide near real-time analytics on that. We also attribute revenue to advertising so that people can buy ads and pay for that with a commission of what they have, what revenues come in. So we try to referee that marketplace. We focus on making sure that people who buy advertising do so with a certain amount of accountability and transparency in terms of what you pay for. That generates a lot of data. So I'll be going through our environment relatively quickly. Then I'll talk about challenges and solutions. And finally, then some conclusions and some takeaways that are probably applicable to a very large number of environments. So basic facts about us: we are a Go PostgreSQL Kafka shop. We have now almost 300 employees, so we are growing rather fast. Our core business is linking advertising events to installations or revenue events. And for this reason, we effectively operate at a big data scale. We have large amounts of data that comes in that we have to aggregate and work with. And so our data is definitely big data. Just how big? Again, this was from January. Over 100,000 requests a second. Nowadays, 100,000 requests a second is the least we see in a day. So our slowest point in the day is 100,000 requests a second. Our fastest point in the day is 300, 400,000 requests a second. And we have seen sustained traffic of 500,000 requests a second under certain circumstances. 2 trillion data points tracked in 2017. I don't know what the figure will be for 2018 yet, but it should be quite an increase from that. Right now we're at over 600 terabytes of data to analyze, so you can see that's about 50% growth in 1 year. And that data comes in at this really high velocity, and the velocity is actually the biggest problem we deal with. As I go through our architecture, you'll see we can get rid of most of the volume problems, but the velocity problems are still there. So here's our general architecture. Requests come in via SDK events from mobile devices on the internet. They get routed in that first arrow via a load balancer that goes to any one of our initial backend processing systems. Those then record the data locally. We then have another process which basically does a MapReduce on that data and sends it to a sharded analytics environment. And finally, we have another service that runs on those shards called the KPI service that aggregates that, does another MapReduce, and sends it to the clients. We have a slightly different architecture than most people are, with slightly different infrastructure rather than most people are used to. We run almost everything on bare metal Gen 2. Our ops team does a huge amount of A/B testing, this kernel scheduler versus that kernel scheduler, this storage approach versus that storage approach, this amount of memory versus that amount of memory. And as a result, we estimate roughly 50% more throughput than we would typically get from, for example, Debian on standard hardware. We also do all of this on standard Postgres with our own extensions and some community extensions. We, interestingly enough, don't use Citus. We don't use any of these other sort of sharded solutions, partly because our infrastructure predates when a lot of these were stable. So data comes in from these mobile devices through the internet to our load balancer, and they're sent back to these backend servers. These are original points of entry. They run a Go-based program that actually processes and sends a response back out, kind of determines probably where an advertising attribution should go, and then records all this data locally. These systems have approximately 20 terabytes per backend. We've actually managed to cut it down a little bit in the last 11 months or so by moving some data into cold storage. And right now we have 28 backend servers in Frankfurt and another 20 split between Amsterdam and Los Angeles. So we actually now have 48 backend servers. So that gives you an idea of the scale of growth that we're doing. So between the backend servers and this sharded data warehousing environment, we have what we call the Materializer. Basically, what it does is it runs an incremental MapReduce on the data we come in, and we process as it comes in, and then it sends it out quickly to these shards on the sharded data warehouse environment. So it runs every few minutes. It's new data only. We don't re-aggregate everything unless we're backfilling metrics. And basically, it copies all this data over to the shards. We're going to talk in a few minutes about really the big challenges we've had in that process. But conceptually, it's worth noting that Materializer is basically just a MapReduce job. Here's a diagram of MapReduce. How many people here are not familiar with MapReduce? Just a show of hands. Anybody? A few? Okay. So the idea of MapReduce is that what you can do is you can run analytics on large data sets by running through the original pieces, perhaps pieces in parallel, and both filtering and transforming from one value to another value. So you can filter them out, you can transform from one value to another value. Then you can run through the shuffle phase, which is in the middle there. And what that basically does is that sorts things into different buckets that you want to get data from. And then you can run through a reduce, which is the actual aggregation phase. And then you send output, one value per, essentially one value per reduce bucket. Does that make sense for anybody, or anybody struggling with that a little more? It's a very common technique people use in big data. And basically our system runs this sort of incremental MapReduce in Postgres. And the logic is actually all stored in the database in user-defined functions. Now on the analytics shards, in January these were 2 terabytes each. Now we're at 5 terabytes each. In January we had 16 shards. Now we have 20 shards. So there's a huge amount of growth here. Now, not all that growth is just simple growth. We had a problem in February when we were running out of 32-bit integers. And we had to upgrade a lot of things to 64-bit integers. And of course, that also creates extra padding because the stuff goes on to the end of the table, and you don't have as much control over alignment, and so you lose a fair bit of space actually to padding in these cases. But there's still a lot of growth. The big problem though is that when we go from 16 to 20 shards, what happens is our Go-based analytics software basically does this big merge aggregate. So it goes out, it queries all the shards, it gets back everything in a sorted order, and then it runs through them in effectively one run per shard, and merges all that data in as it does the aggregate. The problem with this is when you were operating at scale, this is very, very, very hard on the garbage collector. So we are trying very hard not to put more shards in, because the garbage collector just gets more and more behind, and that's actually our biggest pain point. So the analytics shards are paired for redundancy. So shard 1 has a replica of shard 2. Shard 2 has a replica of shard 1. But they also have their own masters. So this allows you to effectively have 20, each with a copy on another one system. Storage-wise, the primaries are on NVMe, and the replicas are on SSD. So we're getting into this. Now, we've actually largely solved the staffing challenge. So I'm not here to say, come work for us or not. But the issues here are things that anybody who's working with Postgres faces. And so I wanted to take just a couple moments and actually share our experience dealing with the staffing challenges, because Postgres has gotten popular much faster than the data administration community's grown to support it. So in our case, we don't really have room for junior database folks, at least not on my team. It's a really demanding environment. You make a small mistake and 4 hours later something crashes. It might even be customer visible. And so this takes a lot of people who are really well grounded in both theory and experience. And finding those people we found initially to be very difficult. What we found that really worked was that we would look for people who could effectively come into the environment and be conversational within, a very short time. So they don't have to be able to contribute, they don't have to understand everything, but they have to be able to carry on the conversations that will help them to learn. You want to be, everybody wants to have their workplace be somewhere where people can grow professionally. And especially when you're in an area where there's an actual hiring difficulty, it's really important to make that a reality. As I say, we've largely solved this challenge for ourselves, but I wanted to leave a few slides in that talk about this for others, because I'd be willing to bet that a lot of other people here are dealing with the same problems. On to the next set of real challenges. 100 to 300 requests per second is a lot of data. This has to be processed. You have lots of Btrees with random inserts. This isn't always very pleasant. Most data is inserted once, and then the same row is updated once. And we have long-term retention. The throughput challenges are actually very big, and they come up in a bunch of different areas. So the first part is that on the backend systems, we have the backend systems designed so that each system can fail as a unit, and we can take it out of production, and the rest of the system isn't really affected. These are the ones which go up to 20 terabytes in size in their database, and basically, if you remove that system from the network, HA proxy will just route to the next one. And maybe that last little bit of aggregation doesn't get done until a little bit later. But if that's 2% of your data, nobody's really going to be knocking at your door saying, what happened to these few clicks? We do pay very careful attention to alignment, and this is actually kind of important. How many here are unfamiliar with the data alignment problems that show up in C in particular? Okay, so because of the way computers tend to work, you don't want reads to span cache pages. Also, you tend to you want to make sure that it's really easy to address things, and so almost everything gets addressed at an offset that's a multiple of its size. So 8-byte integers, 64-bit integers are offset at addresses of 64 bits, right? In Postgres, okay, in some architectures like Intel, you can have unaligned data, but you have a performance hit from it. So higher performance software, including Postgres, make sure that everything's data aligned for you. If you break this, things might fail on certain architectures, or things will get really slow. But the other problem to this is this adds padding. So you can typically find 10, 15, 20% of your space might actually be padding that's induced by data alignment. So if you can cut that down, 10% of 20 terabytes is 2 terabytes. These things add up a lot over millions and millions and millions of rows. Sounds like we're programming in 1985 again, counting bits, counting bytes. But when you're dealing with billions of rows, it adds up. On the analytics shards, we do pre-aggregation to, I think it's a second in resolution. So all the events that come in on a second are grouped together for analytics purposes. They were sharded at 2 terabytes in January. We've put in 4 more servers and scaled these up to, I believe it's 6 terabytes right now. So that's 120 terabytes of pre-aggregated analytics data. Our sharding framework we wrote ourselves, and it's built with the idea that you can effectively have all of your shards give a small piece of their data to the next shard, so it minimizes this issue of rebalancing when you add more shards. So unlike the backends, which store locally processed data, and so you don't have a way of locating data, on the shards we can locate it. We usually don't because the span of aggregates tends to be bigger than what we shard on, but if we need to know where a particular piece of data is, we can calculate on which shard it should be. Now, the Materializer we're going to talk about in a lot more detail in a moment, because this is actually a case where a lot of really important details matter. The Materializer runs in 2 phases. You might remember MapReduce. The first stage is what's effectively the first stage of the MapReduce. It's effectively a full MapReduce cycle itself. We run through the data, we pre-aggregate it, we determine which chart it's supposed to be on, we write it to a temporary holding table, and that's that. On the second phase, currently, we copy that data to the shard, and then we effectively do another MapReduce and apply the changes to the analytic shards themselves. We have, however, a very, very special problem here. In January, we were using the foreign database wrapper for the Materializer. Just as a show of hands, has anybody tried to use the foreign database wrapper to write rows to a significant number of rows to a server that's maybe in another city or anything? Nobody tried this? Okay. The problem is we were writing to a foreign database wrapper, Postgres. What the foreign database wrapper does is it prepares a single statement and it executes it for every row. This means a full network round trip every row you write. If you're writing a few million rows, that works great if the 2 systems are close to each other, connected by fiber optics. It doesn't work so well when one server is in Los Angeles and one server is in Frankfurt. There are, as Grace Hopper would have said, a whole lot of nanoseconds in between. So this was a blocking issue for us. And in the next slide, I will kind of discuss some of the approaches that we took to solving this. So the first, basically we've had 2 or 3 iterations which have all come down to this approach. Basically you have a C program, whether it's running in one of the databases or not, and basically it does a bulk copy, and copy in Postgres is a streaming API. So you can copy data, you get a stream back, and you can write it to somewhere else on another stream. Basically, it's just a Postgres client. You pull data from one place, you put it to another. I wrote an early global transaction manager to manage this so that both sides would commit or roll back together. And this, in fact, worked to restore throughput. We've had a few reasons we've eventually moved to a separate program running on a separate system, mostly because if you have a system go down, you can't really guarantee that you can write everything you need to write in order to figure out what you need to do to restore the transaction. So this has effectively been moved to another program. It's been moved outside the database just because that means that when the database actually has a problem, we can still bring everything back up into a consistent state. So on to the next thing. How many people here are familiar with Autovacuum? A fair number. How many are not familiar with Autovacuum? Okay. How many are not familiar with the problems of garbage collection generally? Okay. So basically, Autovacuum is on-disk garbage collection for Postgres. We want our databases to always be consistent and to move from one visible snapshot to another one without any inconsistencies in the meantime. So Postgres does everything as copy on write. Every update is a copy on write. What this means is you need a garbage collector to go through this and make the space available for future writes. Otherwise, the tables bloat, queries get slow, indexes aren't very useful, and a bunch of other really bad things happens. The problem is Autovacuum has some really some default settings that work, for test environments, but really don't work when you get into larger tables. The default settings, 50 rows plus 20% of the table has to be dead before Autovacuum will start its run. Now, if you have 1,000 rows in your table, that's like 250 rows. It's not the end of the world. But if you have 100 million rows, that's 20 million rows plus 50. And in those cases, you have a really hard time getting Autovacuum to work properly. Anybody here had trouble getting Autovacuum to work because of this sort of thing? Nobody? Okay. So these things are actually really hard. And then what happens is, Autovacuum does nothing, and then it hits the database really hard. The system can basically be saturated, it can sometimes go down. Performance suffers, tables bloat, you run out of disk space, a lot of bad things. So what we did was we changed the settings. We changed the default setting to 150,000 rows plus 0%. Now, obviously, this wouldn't work if you only have 1,000 rows, right? You'll never Autovacuum it. And that would be a problem. But this requires a lot of hand-holding. The first 5 systems we tuned in this regard, 2 of them fell over. And another 2, I had to do a lot of work to keep them from falling over. I tried another 4 systems after that, and they all fell over. So tuning this requires a lot of hand-holding when things are under heavy load. The problem is Autovacuum will say, oh, we have 3,000 tables to vacuum. I can do 5 at a time. Therefore, I'm going to create 5 queues of 600 tables. We'll vacuum those, and then we'll see what needs to be done. 3 days later, system falls over. So the end result was I wrote a little bash script that went through and did what Autovacuum was going to do. And I just let it run for a couple days, and then I tuned it, and everything worked just fine. So the next thing is about data schemas and so forth. Data modeling and schemas are really important. Under heavy load, they're very, very, very painful to change. These require some really heavy locks. And if you do something that requires rewriting a table, it has to rewrite that table while that lock's held. At the same time, we also want to minimize disk usage. We don't want to just say, oh, well, we could do anything here, and so we store everything as text, and we store a lot more ones and zeros than we have to. So we want to maximize alignment to pages. We want to make sure we can store as many rows in a page as possible. And so a lot of these little details really matter. Data modeling is actually one of the bigger challenges that we deal with. One of the tools we use in this are custom 1-byte enums. These are little C programs that basically store a whole bunch of basically numbers and text representations. And for this sort of thing, basically you can store all the countries in an 8-bit integer. So we do this for languages. Obviously, there aren't enough bits in 8 bits to store all languages, so we store all the languages we're interested in. All OS names, all device types, and so this means that instead of Linux taking 1, 2, 3, 4, 5, 6 bytes, no, 7 bytes, because you have the length, this is a varvarlena, it only takes 1. Again, over millions and millions of records, this is a really, really big win. Another thing we make is this type we call Istore. This is not related to the Apple Istore, it's a complete different thing. This is like HStore, so it's a key value store as a type. But this is integer to integer. And the neat thing about this is then we can add them together. We can use it to model time series. We can use it to do various other analytic stuff. And basically, we use this where a lot of other people would use columnar storage. So basically, we do this big incremental MapReduce. On the backends, it sends it to these KPI shards. The KPI shards do another incremental MapReduce. And then when we send the data out to the client, we do another MapReduce via the web service that provides this data. So I just want to say just a few brief things about operational stuff. And then I'll get to conclusions, and I'd like to take a little bit of extra time for questions and answers. For our main operational tools, we use Sketch for managing database changes and migrations. Rex is Perl-based tooling around SSH. It's kind of similar to Puppet, if you will. And then we write a lot of our own custom tools. Backups. It's a homegrown system. In January, I was told when I was first looking into this that it was base backup plus wall. It turned out to be nightly PG dump. One of those things, you have to restore your backup to find out what's in it. We can also do base backups, but we don't really do them. The thing is, this doesn't work really well. And with the amount of traffic we have, we find that for every 1 terabyte we have in our analytics shards, we generate about half a terabyte of wall. So for 100 and some odd terabytes in the analytics shards, that's 50 terabytes of wall. It's actually really hard to maintain a good backup and keep that manageable and so forth. So we've actually started writing our own tools here. We wrote our own tool that basically connects as a logical replica and streams changes out into change sets. So this is an area where our environment has actually changed quite a lot. Finally, ongoing distributed challenges. Major upgrades are a big problem. Obviously, storage space is something we struggle with quite a lot. As I mentioned before with the Materializer, multi-data center stuff starts getting actually really, really hard. And very oftentimes when you're dealing with these really hard things like the multi-data center challenges, it may be 2 or 3 tries before you actually have something that works. Of course, making it all fast is another ongoing challenge. So into the conclusions section a little bit. Our environment is one where we have a lot of systems, a lot of attention to detail, a huge amount of things that can go wrong, and things which require a huge amount of attention to detail. A lot of gains may seem like they're really small. You save 5 bytes here, 10 bytes there. But if you can save 15 bytes in each of 3 billion records, that's actually a lot of space that you've saved. So we actually use Postgres as a big data platform, in case you haven't noticed. Things span well beyond one machine. We expect this architecture to scale pretty much as far as we need to. And it provides near real-time analytics to our clients. Our current time from when something shows up in the backend server to when it shows up in the dashboard is on average between 5 and 10 minutes right now. So we promise within an hour, but usually it's within 5 or 10 minutes. So one of the very interesting pieces here is that compared to everything else we work with, we're actually most comfortable scaling Kafka and Postgres. Almost everything else we work with, we have scaling problems with. But by separating things out and being able to build these distributed environments, we largely avoid most of these issues. And I just kind of want to take a very quick detour on this last slide onto an example here. Also in January, we had a Elasticsearch cluster that crossed the 1 petabyte line. And at that point, Elasticsearch became very chatty, and the chattiness could actually take down nodes. It could actually take down the whole cluster. We redesigned that 1 petabyte system in Postgres using the same sort of sharded approach. And the sorts of problems that we ran into went down quite a lot. We went from lots of outages to almost no outages. I told the head of ops what I was trying to do for testing data retrieval, and it's like, if you were doing that on Elasticsearch, you would have killed the cluster. And I'm like, well, everything hummed along fine here. And that cluster is now 3.5 petabytes. It's architecturally not as interesting as this one, but it shows how far we can take the same expertise and make everything scale. So with that in mind, I want to thank everybody and start taking some questions. So I have a little bit of extra time for questions and answers.
Thank you. We do have quite some questions, so how about we start from the first one? What's your feedback on the approaches of the big data-centered PostgreSQL forks by the community, such as Greenplum, for big data analytics? What experience working with these can be shared?
Okay, so I spent a lot of time talking with the Greenplum people, and I expect to spend a lot more time speaking with the PostgreSQL people as well. Greenplum, by the way, is now open source, but they've done a lot of things to sort of make it really work well for analytics. I guess what I would say is in every single one of these cases, you want to make sure that you understand what the underlying assumptions and models are. I've watched people talk a lot about PostgreSQL, and PostgreSQL is a really great project, really promising. For some things, we're considering possibly implementing it. But I've watched people also say things like, well, you can do multi-master replication and keep it fast. Well, that's not true. People make that mistake because they think just because one thing's fast means that you can use every piece of it fast. And in the case of multi-master, when you have a table that you're replicating multi-master, that's going to be as slow as your slowest link, and you replicate those ones that you're writing to very seldom, but you're joining against very frequently. So what I'd actually say in all these cases is that when you're using one of these or when you're building your own, you really, really have to understand what the limits you're dealing with are so that you can build around them. I don't know if that's sufficient, but if not, talk to me outside.
Or on the party, right? Best place to discuss Postgre. Why not Hadoop, Spark, etc.?
Okay, so so that's actually a really good question, and I think Spark could be very interesting in certain use cases for our data scientists and such. Hadoop is less so. Hadoop, my experience with Hadoop is basically that it thinks in terms of these HDFS blobs. That's really great if your data kind of needs that sort of model. But relational databases work really well when you're modeling everything with small tuples, which are mathematically, which mathematically can be quickly aggregated. And so it's going to be very hard to get Hadoop to perform as well as we get Postgres to perform in these regards. We lose some of the tooling around Hadoop, but we gain a lot of the performance optimizations that the Postgres community has pushed in.
Cool, thank you. You used a lot of hacks to optimize performance. Are you sure that PostgreSQL is the right technology for you and your problem was not solvable much easier with other techs? Did you consider to change it to something else?
That's actually a really great question. So anytime you're building a big data platform, you're going to have things you thought about at first and things you didn't think about at first. When I was working on a previous project that ended up using Hadoop, the advice we were given by Hortonworks was, you build your first cluster, you try it out, you build your second cluster and hope it works. So these problems aren't limited to Postgres. They in fact affect almost any time you're working on these sorts of scales. I guess what I would say about this is the problems at this scale are so individual that you're probably going to have to do some performance hacks somewhere anyway.
Do you use transactions or joins with Postgres?
We have more or less avoided joins for most of our work. We do use transactions, and in fact, we use two-phase commit. But we don't use. But we have avoided joins for most of our work. Some things, in fact, we do use joins for, but they're the exception, not the rule.
What is the benefit of Btree for your tasks? Why not to use plain logs approach? There are no inserts struggling.
Okay, so when we do these incremental MapReduce jobs, we need to quickly identify the new rows that we need to access. So we use a Btree index to point at the tuples in Postgres that we need to aggregate, and then we aggregate those and move them over. And then when we set them as materialized, they drop off that Btree. That allows us to store these inline in the same heap tables that basically store the archive information. There are other ways of doing many of these things. You could have one holding table and then you could aggregate it to another table. In fact, we do that in one of our other environments, but at least as far as this particular environment, this is the best solution we've come up with.
Great. What would you change in the setup if you had to build this whole thing from scratch for a similar volume of data, as opposed to evolving the system along with the business demand?
That's another great question. I think there are 2 or 3 things that I would change. Probably the biggest one is that when you're operating at a really high scale, garbage collected languages are a bit of a pain. So I would probably see what we could do to move this analytics software from Go into C, as strange as that might sound. The second thing I'd probably change is the fact that when we do these incremental MapReduces, we have all this stuff to quickly find these rows fast. I would probably change the way we do that to use some sort of a holding table and a join instead of an index that's going to have a whole lot of really heavy update maintenance. I'd also probably try to have the Materializer send stuff over Kafka to decouple things. That would avoid two-phase commit, and probably there are some other things I could think of.
Great. How do you manage all this infrastructure on the bare metal, and how much of human overhead you have to support it?
That's a great question. We have 7 ops people who are fully working now, and we're training 2 more. They manage somewhere 500, 600 bare metal servers. We try to optimize for human effort as much as possible. But we also optimize for server costs, because when you have even 9 admins and you have 500 bare metal servers, and those servers are taking up a lot of space in a data center, your primary cost there is going to actually be data center space. So we would be quite happy to be able to optimize that by hiring more people if we had to. But as I say, currently, 7 or 9 people able to manage all of this, it seems to work okay.
All right, so then where is your hardware? You own it, rent it somewhere? How do you manage it?
So we rent space from a data center, or from a couple of data centers owned by the same company, and then basically we buy the hardware and put it there. So we have our biggest data centers in Frankfurt, and we're moving from one data center to another data center in from the same company right now. Then we have a bunch of systems in a data center owned by the same company in Amsterdam, and then a smaller number of servers in Los Angeles.
All right, and maybe we have time for one last question.
Mm-hmm.
How do you even begin to approach a major version update at this scale?
That's a great question. Different components get updated in different ways. What we did for the backend servers is we actually just installed a new version of Postgres, and then we just made sure we got the schemas in place, and we just then flipped the ports. Because that's just basically a log, we can do that, that's easy. For the analytics shards, that was much harder. What we did there was we basically failed over everything to the read replicas, and then we ran PG upgrade on the main systems. The big problem is we can't write to anything while we do that, and then we have to rebuild the replicas, and so you have some points where if a server goes boom, maybe you lose some data. So that part's much harder. The initial point of entries sections was much easier.
Sounds quite overwhelming. Thank you so much for answering so many questions.
Thanks.